Hello, everyone. I am Professor Wa from the Communication Engineering Teaching and Research section at Wuzhou University, and welcome you to this mini lecture. Today we continue with Chapter 4, Frequency Domain Analysis of Signals, focusing on Section 4, Properties of the Fourier Transform of Continuous Time Signals. In addition to the definitions of the forward and inverse Fourier transforms, the Fourier transform has many important properties. These properties have broad applications, as they reveal the inherent connections between the time domain and the frequency domain of continuous signals. They also help deepen our understanding of both the mathematical and physical concepts of the continuous time Fourier transform, and play a significant role in both theoretical analysis and engineering practice. In what follows, we will discuss several commonly used fundamental properties. The Fourier transform is a linear operation, which means it satisfies homogeneity and superposition. This can be judged and applied using what we learned in Chapter 1, as shown in the following mathematical expression, where A and B are constants. Similar to the even-odd decomposition of real signals, a complex signal can be decomposed into conjugate symmetric and conjugate antisymmetric components. Regarding conjugate symmetry, you only need to remember two main results, as given in the following two equations. Namely, the Fourier transform of the conjugate of f of t is the conjugate of f negative j omega, and the Fourier transform of the conjugate of f of negative t is the conjugate of f j omega. In addition, you should remember an important conclusion. The conjugate symmetric component FET and the conjugate antisymmetric component FOT of a signal f of t correspond respectively to the real part FRJ omega and the imaginary part Fij omega of its Fourier transform Fj omega. There are many other important results concerning conjugate symmetry. However, due to time limitations, I will not elaborate further here. Please refer to the relevant textbooks for self-study. The time shift property of the Fourier transform is mainly applied to solving the spectra of delayed signals. Its mathematical expression is shown below, where t0 is any real number. One important point to note is that a time shift in the signal domain corresponds to an additional phase shift in the frequency domain, while the magnitude spectrum remains unchanged. The scaling property states that compression in the time domain leads to expansion in the frequency domain, and stretching in the time domain leads to compression in the frequency domain. The mathematical expression is shown below, where A is a non-zero real number. Let's look at an aperiodic rectangular pulse as an example. Observe how the scaling property appears in its spectrum in the figure. Notice that this pattern is the same as what we saw earlier for the impulse and DC signals. In communication systems, it is often necessary to increase the transmission rate, which means reducing the width of the rectangular pulse signal. This, in turn, requires expanding the effective bandwidth of the communication equipment. The duality property concerns the interchange of waveforms between the time domain and the frequency domain. The mathematical expression is given below. Pay attention to the variable exchange and the scaling factor. Also, take a look at the figure. Observe how the aperiodic rectangular pulse and its spectrum essentially swap roles. Be sure to note the labeling of the axes in the time and frequency domains. Let's take an example to deepen our understanding of the duality property. We want to find the spectrum of the signal f of t equals 1 over pi t. This can be derived using the Fourier transform of a sine function. By applying the duality property, we can interchange the sine function sgnt with its spectrum 2 over j omega, and then adjust the coefficients accordingly. From this, we obtain the spectrum of f of t. The frequency shifting property is a fundamental theoretical basis for modulation techniques in communications. Its mathematical expression is given as follows. When a low-frequency signal f of t is multiplied by a high-frequency complex exponential signal of frequency omega 0, the corresponding spectrum of f of t is shifted in the frequency domain by omega 0, while the shape of the spectrum remains unchanged. Based on this principle, a low-frequency signal can be shifted to a higher frequency band for transmission. In practical applications, the signal f of t is often multiplied by a sinusoidal signal. As shown in the two derivations below, this results in the original spectrum being shifted to both the left and right, with the amplitude reduced by half. Now, let's observe the spectrum of a rectangular pulse signal f of t when it is multiplied by a sine signal. As shown in the figure, the result is fully consistent with the conclusions we just discussed. The time domain differentiation property states that when a signal is differentiated in the time domain, the corresponding operation in the frequency domain is a multiplication. Mathematically, this means that for the nth derivative of a signal, multiply f j omega in the frequency domain by j omega raised to the power of n. Please note, this property has important applications in frequency domain analysis of electrical circuits. For sinusoidal circuits in particular, it can significantly simplify the calculations. The frequency domain differentiation property allows differentiation in the frequency domain to be converted into multiplication in the time domain, which also serves to simplify calculations. The mathematical expression is given in the formula below. The time domain convolution property shows that the Fourier transform converts convolution in the time domain into multiplication in the frequency domain. The mathematical expression is as follows, where the symbol asterisk denotes convolution. The frequency domain convolution property states that the Fourier transform converts multiplication in the time domain into convolution in the frequency domain. The specific formula is given below, with special attention to the scaling factor 2 pi in the operation. The integration property states that integrating a signal in the time domain corresponds to dividing its spectrum by j omega, with the addition of an impulse at zero frequency, whose strength equals pi times the signal's DC value. If the signal has no DC components, then f0 equals 0. For a non-periodic real signal, its energy can be computed either in the time domain or in the frequency domain. According to the principle of energy conservation, the two results are equal. This result is known as Parseval's energy conservation theorem, expressed mathematically as shown below. At this point, we introduce a new physical quantity, the energy spectral density function, which represents the signal's energy per unit angular frequency. Its mathematical definition, g omega, is given below. Please note, the energy spectrum is an even function of omega. It depends only on the magnitude characteristics of the spectrum and not on its phase characteristics. We have now briefly reviewed several important properties of the continuous time Fourier transform. These properties are widely applied in spectral analysis of signals. By combining these properties with the spectra of commonly encountered signals, we could determine the spectra of more complex signals and thereby carry out frequency domain analysis. For convenience, the properties in their corresponding mathematical expressions are summarized in the table below, so that you can organize, review, and memorize them more easily. Please reflect on today's lecture and complete the following homework exercises to consolidate the concepts learned and deepen your understanding. That concludes today's mini lecture. See you next time.